the case 2 of application happens when I linearize at, for example, an equilibrium or a periodic orbit. Why am I using this? So, linearization at equilibrium and periodic orbit. So I believe that you taught Floquet theory, right? So one of the most powerful ideas of dynamical systems is that there are certain special solutions of your equations such that nearby the dynamics can be qualitatively studied by studying the linearization, right? Now, what's the linearization of this equation 2 at, for example, an equilibrium? Well, one can prove that the linearization comes given by differentiating f in the first, g in the first component, or periodic maybe solution x of t, by differentiating g in the first component first, and then differentiating in the second. And naturally, this equation comes up, and this is g, sorry. This equation comes up by applying chain rule to the interior of E, but one has to justify that the solution semi-flow of this new equation is actually the Fréchet derivative of the semi-flow of the nonlinear equation 2. But you can find this in any books. And now, naturally, this is again A of t, and this is again B of t. So it will turn out that the zero number is telling me something about the eigenfunctions of the linearization at these special points. Why? Well, for example, let's think of, let's say that I have an eigenfunction, right? Let psi of t be an eigenfunction. Then I have that psi of t plus a certain value, right? Maybe the period of the periodic solution I'm linearizing around. So this is the period of x of t. Let's say that I get out mu times psi of t. So as I move forward, I'm just multiplying by a scalar and getting back the same function, right? So this tells me something about the zeros of the eigenfunctions, right? For example, can an eigenfunction have multiple zeros, like a double zero? Only, quick answer, only if the zero number is infinite. Why? Because if it has a multiple zero, then this condition 4 is telling us that it must be dropping zeros constantly. But still, I can recover the position of the zeros by shifting forward. Yeah. Because when I shift forward, I'm just multiplying the function by a scalar. So I always have the same number of zeros. They shouldn't drop, yeah. Right? Yes. So you see, this is the kind of power that comes from having these properties. It tells me something about eigenfunctions in this case, and it will also tell me something about differences of solutions. But I will not stick. So the main consequences are the following. So the consequences that I will foreshadow now are from C1 that the most important dynamical objects of 2 are periodic solutions and equilibria, and from C2, a sort of Sturm-Liouville eigenvalue structure, but for delay equations. Do you know Sturm-Liouville? Yes. Yes? So who knows Sturm-Liouville from, say, PDE or ODE courses? This is very traditional. Very.
You can write and let me explain.
Yes.
So 你考虑二阶合成算子 due prime Sturm-Liouville operator， 那你知道它的 eigenvalue 都怎么样 ？simple， 是 self-adjoint。然后实数，然后它的 eigenfunction 有 model property， 第一个 eigenvalue 对应到 eigenfunction 就0个 0 1个 2个3个4个，这个叫 Sturm-Liouville oscillation property， 对啊。然后你可以做 Sturm-Liouville comparison， 这就 ODE 的 book 都会教了，你用 Sturm method。他的意思说，现在因为有那个 dual number v，DD 也有差不多的 property， 你只要有这个 Sturm-Liouville property， 你的 dynamic system global dynamic 都可以有很好的刻画。Please.
Yes. So essentially, this Sturm-Liouville property will be a relation between the size of the eigenvalues associated to an eigenfunction and the number of zeros, so V of psi t that they possess. And it will turn out that the faster they oscillate, the more stable they are. So the larger the number of zeros, the smaller the value of mu, or the absolute value of mu. Okay. So for the remainder of the talk, I wish to focus on this consequence of C1 rather than the consequence of C2, but I think it's good you know that, yes, actually you can say something about stability of periodic solutions in systems like 2, about linear stability of periodic solutions in systems like 2, thanks to this second property. And maybe I will talk about this a little bit more in a discussion towards the end. But for now, let's focus on this first point. So let me erase this. Yes. So let me keep a recap. So the connection between 1 and 2 is that differences of solutions of 2 solve 1, where this should be understood as solve an equation of type 1. And eigenfunctions of linearization at equilibria or periodic orbits of 2 also solve 1. Yes. So now I would like to introduce one small thing, which is the definition of omega limit set. I believe this is already from the homework assignment, but maybe let me include it here. Yes. So definition, the omega limit set of a bounded solution defined on all of R, just in case, of 2 is omega of, let me write down here, x0. Yes. So this is the initial condition. This is functional differential equations notation. You have been using this, right? So this is the prehistory, yes. Yes, they are the elements in the space of continuous functions. So -1, 0 to R, such that there is a sequence Tn to infinity, such that limit with Tn to infinity of, careful, T was temperature before, but you also use T for solution semigroup, right? So this is the solution semigroup, semiflow of the 2. And now do you put it in brackets or?
With bracket.
With bracket? Okay. X0 here. Or do you put comma? What do you prefer?
No comma.
Okay. I just want to stick to your notation.
Converge to.
Sorry. Phi. Yes. So, yeah. Yes.
I also specify.
Sup or infinity. Yes, so in the topology of the Banach space under consideration. So essentially these are the points such that there exists, so they are the points such that the solution curve, if you think of x sub t, right, as a curve of functions, these are the points such that this curve of functions is accumulating to them. So for example, if I have, let's say that I pick a prehistory which is an equilibrium of 2. What's the omega limit set? What's the omega limit set of the equilibrium? Well, T of x0 is x0, right? For all values of t. So the only element that lives in here is x0 itself, because you could pick your favorite sequence, 1, T1, T2, T3. Okay, say that now I'm a periodic solution. Then what's the omega limit set of a periodic solution?
No, we are very shy.
Yeah, I know, but I want to push you a little bit. Come on, guys. Let's say now that
draw a picture, maybe.
That T, yeah, I mean, and this definition is valid regardless if I'm doing delay equations or I'm doing ODEs, right? So for example, if I do ODEs on the plane, a periodic solution is just a circle, right? And here I have Y. And I pick an initial condition here, and I start moving forward, and then I come back here. And then after time 1 period, P, I do it again. So what's the omega limit set? Like for example, can I accumulate to this point here? Can I find a sequence of times such that I accumulate to this point? Well, I could, if this is x sub 0, right? Maybe this is x sub 1. Maybe it takes me time 1 to get here. And after, and x sub 1 plus p is what? Is the same value, right? This is x1 plus p, 1 plus np, and so on. So I accumulate, I pick one point here. I can get to this point after a finite time shift. And then after p plus np and so on, I'm still at this point. So I can find a sequence that accumulates to that point. But there are more complicated situations, right? Say that I start, let's do things in the plane. Let's say that maybe this point is a source, and out here I have a heteroclinic loop like this. And this is a source, and there is nothing in between. So then what's the omega limit set of the source itself? If I pick my point right here. Well, it's a bit of a trick question. The source is an equilibrium. So the omega limit set of this source, of the source, is x0 itself. But if I start somewhere in between, if I pick my x0 here, then as I move forward, I will start to come closer to this I, right, to the heteroclinic loop. And then in the limit, well, I will start to get closer and closer and closer, but never quite reach it. But it's still clear that the trajectory is accumulating to the I, right? So I can always find a sequence of times such that the trajectory, such that a point on the orbit, on the forward orbit, is accumulating to this point, for example, to this equilibrium. And I can always find a sequence of times such that the trajectory is approaching to this point. And I can also find a sequence of times such that the trajectory is approaching this other point here. So the omega limit set will be the whole I. But now, how about points on the I itself? What if the I has dynamics like this, for example? So if I start on the top, I'm moving to the left, and if I start on the bottom, I'm moving to the right. What's the omega limit set of a trajectory here? Yes. If I start here on the bottom, I will eventually flow to the right equilibrium, and if I start to the top, I will eventually flow to the left equilibrium. Yes, precisely. So it turns out that these omega limit sets, and by the way, the notion, the nomenclature or the name omega itself is a very Christian Catholic thing, maybe. This is because of, Jesus Christ says, I'm the Alpha and the Omega. Okay. It's not, no? Who says this? Jehovah is the Alpha and the Omega. Okay. And God is the beginning and the end, because Alpha is the first letter of the Greek alphabet and Omega is the last letter of the Greek alphabet. So Omega is like the end of your trajectory. That's the reason for this choice. And Alpha, if you do this backwards in time, then you have the alpha limit set. But today we focus on this. This is just so you remember. Why are we interested in these guys? Well, there is something called the fundamental theorem of dynamical systems. So why omega? There is something called the fundamental, or Conley's fundamental theorem of dynamical systems, which goes back to Charles Conley, I believe, but I cannot give you a date or a precise reference. And this tells you that the dynamics split in two. So dynamics on a global attractor, on A, split into a recurrent set. That's trajectories that eventually come back, so points that eventually come back to a neighborhood of themselves, essentially. So you take an initial condition, and as you iterate it forward, it will come back somewhere close to the point. And then if you iterate it forward again, it will revisit. So this is what's called a recurrent set. And there is also something called, maybe let's call it transient set. So the recurrent set is the non-wandering set. So there is a splitting of the dynamics of a system into a conservative part that doesn't move too much from its origin, and a dissipative part that tends to decay. And if you pick an initial condition on the attractor, you're either here or you're here. And it will turn out that the omega limit sets of orbits are all contained in the recurrent set. So the goal is to describe one of these two fundamental objects of the dynamics of an attractor. Okay. And maybe we can stop here before I start something else.